Welcome to ES 310, Lesson 16. Today we're going to extend the work we have been doing with impulse and momentum in the linear directions to include motion along curves or in circles. So we're going to introduce the concepts of rotational momentum and rotational impulse, and then also look at the conservation of rotational momentum. In order to do this, we're going to have to review moments and cross products, which we've seen in statics. More information on this topic can be found in Hibbler's Dynamics textbook, Chapter 15, Sections 5 through 7. So let's start by reviewing moments. If you remember from statics, a moment is an action on a body that causes a rotation. So just like a force is an action on a body that causes linear motion, moments are actions on bodies that cause rotations. Mathematically, a moment was the cross product between r, which is the distance from the point of rotation to where a force is applied, crossed with f, which is the force. The direction of a moment is perpendicular to both r and f. So usually you see r and f drawn in the plane, so the moment is perpendicular to that plane, coming out of the board or into the board. If we are using a right-hand rule, we put our fingers along the r, we bend them to the f, and our thumb points in the positive direction for the moment. If the object is rotating counterclockwise, it's positive. If the object is going to rotate clockwise, it's negative. A couple is a special type of moment which is created by equal and opposite forces. It's often in problems that we see that a couple is applied by an external motor. Something external to the system is causing rotation, and it's put on our diagram as a external moment or a couple. We need to review how to solve cross products, since a moment is the cross product of r and f. So one way of solving the cross product is to say that the cross product of A and B that has an angle theta between A and B is equal to A times B times the sine of theta. We have to then keep track of the direction of that theta, though. That theta has to start at A and go to B in order for this to work. You could also use vector math to solve for your cross product. So if you remember, we set up the matrix with the I hat, j hat, k hat, and we usually extended that. So we just repeat the I hat and the j hat columns. Ax, ay, bx, by, right? And then our vector math version of A cross B is I hat, A times ay times bz minus az times by. Then j hat az times bx minus ax times bz. And k hat ax times by minus ay times bx. Gives us our vector notation version of our cross product. Notice the cross product results in a vector, right? So we still have an I hat, j hat, and k hat components to this vector. What we have up here, this is the magnitude of it, right? And our direction is then given by the right-hand rule over here. So now let's look at moment and angular momentum. So angular momentum can be thought of as a moment of the linear momentum. So linear momentum is m times v. This is what we have been calling L. If we cross R with L, so R crossed with L gives us the angular momentum, which we're going to call H. All right, so R crossed L is equal to H. Now we want to be able to relate this angular momentum to the moment. To do that, we do a little bit of math. Let's take our definition of angular momentum and take the time derivative of both sides. So we get h dot, which is the simpler version of writing the time derivative, and then we've got the time derivative of a cross product. So just like the product rule, right, we're going to take the derivative of the first times the second, plus the first times the derivative of the second, and then we look at each of these terms more closely. Well, r dot is just v, right? So here we have v crossed with v, which gives us 0, because if you cross two vectors, there is no component perpendicular, so two parallel vectors crossed with each other always gives you 0. And then your second term over here is r crossed with m v dot. Well, v dot is just a, right, the acceleration, so m times a is the force, right, by Newton's second law, force is equal to mass times acceleration. So this is r crossed with f. Well, r crossed with f is by definition the moment. And so what we've said then through this analysis is that the time derivative of the angular momentum is equal to the sum of the moments. This is equivalent to saying the time derivative of the linear momentum is equal to the sum of the forces. Both of these are just ways of rewriting what we've already seen as our impulse momentum equations. So here's a look at our impulse momentum equations, right? We have the impulse, which is the integral of the force dt, right, is equal to mv2 minus mv1 is one way we've seen it written. Or mv1, that's the initial momentum, L1, plus the impulse is equal to the final momentum. In the angular direction, we've got the angular impulse, so that's the time derivative of the moments instead of the forces, and that's going to equal the change in the angular momentum. And these are, you should be able to see, here we've got the integral on the f and the moment. Here, this is the same idea, but we've got a derivative on the momentums instead. So let's take a look at how this might work in an example. So this is impulse momentum, but it's rotational because this little car is going to be moving in a circle. So let's see what we're given here. We're given that the car is on a rod and the rod has negligible mass, so we can still treat the car as a particle. It's subjected to a couple moments, so there's some motor here at the center that's creating a moment, and that moment has the expression 30t squared. Then the engine in the car itself also produces a force, which is at a distance of 4 meters, so that force is going to create a moment as well around this shaft in the middle. We need to figure out what the speed of the car is at t equal to 5 seconds. So after this moment and this force has been applied to the car for 5 seconds, how fast is the car going? And we're given the total mass of the car. And we're told we can neglect the size, so we're going to assume car is a particle. Because all of the things we've learned so far only apply for particles. Alright, so the equation we have is initial momentum, angular momentum, plus the angular impulse, which is the integral of the moments, dt, is equal to the final momentum. We are told that the car starts from rest, so the initial momentum is 0. All right, angular momentum or linear momentum. The initial momentum is 0 if the car starts from rest. What is the sum of the moments on this car? So we've got the moment that's being applied by the motor plus the moment that's being applied by this force of the engine in the car. So we've got integral, and we have 30t squared, that's this moment, the couple moment, plus 15t, that's the force, times the distance is 4, and those are always going to be perpendicular. We don't actually have to take a cross product, they're already perpendicular, so we can just multiply them together, times dt is equal to the final momentum. So the final momentum is r crossed with mv, right, angular momentum. Well, r is 4, and we've already said r is already perpendicular to v, right? So that's what a cross product does, is it finds if they're perpendicular, it's very easy to find cross products. So times the mass, which is 150, times the velocity, which is what we're trying to find. All right, so let's do this, and our time period is 0 to 5. So there's our integral. All right, so the integral of 30t squared dt is 30 divided by 3t cubed plus 15 times 4 is 60 divided by 2t squared, evaluated from 0 to 5, is equal to 600 v, and we can solve for v to be 3.33 meters per second. As a second example, our forces are going to get a little bit more complicated, and we're going to end up having to use the normal tangential coordinates because this block is moving in a circle. So we have a 10-pound block, originally at rest, so H1 is equal to 0. It's on a smooth surface, so there's no friction. It's acted upon by a radial force 2 pounds, right? So there's that one. And a horizontal force of 7 pounds that's always 30 degrees from the tangent. And there's a cable here in the middle, right, holding it to the center, and we're asked to figure out how fast can it go. Well, how long can these forces be applied before the cable breaks? And how fast is the block going when that occurs? So, and we can neglect the size of the block, so the block is a particle. Alright, so if we look at the block, what forces are acting on this block? Well, here's our block. Looking at it from above, we've got the tension, we've got 2 pounds, and we've got this 7 pounds at an angle here. So that's 7, and we have this. Alright, so this is 30 in here. Alright, so let's use the NT coordinate system. Since this thing is moving in a circle, that's easier to do. So the forces, sum of forces in the tangential direction, there's just one, right? There's the 7 times the cosine of 30 in the tangential direction. In the normal direction, we have sum of forces is equal to, well, we've got the tension, which we say it will break at 30, so the point we're interested in is when t gets to 30. So positive direction is towards the center, right? So this is the positive t. That's, oops, sorry, they're switched. That's the positive t, and this is the positive n. All right, so in the normal direction, we have the tension is positive. We have a -2, and then we have a -7 sine of 30 as the component of this force that's acting normal to the path. Okay, so we remember sum of forces in the normal direction is going to equal mass times v squared over rho. So that should allow us then to find v squared, because we know the mass, we know the radius. The radius is 4, the mass is 10 divided by 32.2. So we get 30 minus 2 minus 7 sine of 30 divided by the mass, which is 10 divided by 32.2, times the radius, which is 4, is equal to v squared, so v becomes 17.7. Alright, so we now know that at the point where this breaks, the block is going to be moving 17.7 feet per second. So that gives us enough information to find the final angular momentum, right? So the final angular momentum is r crossed with mv. Well, r crossed with v normal is going to be 0, right? Because they're in the same direction. R crossed with v tangential is going to be we can get rid of the cross, so it's r m v t. All right, vt is what we just found. Is this 17.7 feet per second, because the speed is in the tangential direction. So we get then r, which is 4, mass, which is 10 over 32.2, times 17.7. Our impulse momentum equation then says that h1 plus the impulse, angular impulse, has the moments in the integral. Let me make that look like an m. dt is equal to h2. Alright, so what is causing this moment? Well, the only force that's causing a moment is this tangential force, right? Because the normal forces don't cause a moment because they're parallel with the radius. So the tangential force is 7 cosine of 30. The moment is created because there's a radius of 4. So that's the radius, or this is the moment. dt, the integral dt, so that's just times t, is equal to 4 times 10 over 32.2, 17.7. So the only unknown is t, so we can solve for our time and get 0.91 seconds. So, quick review. We have the impulse momentum equation. We know our initial momentum is 0 because it's not moving. We have information about our final momentum based on sum of forces in the normal tangential. And so we can find the speed for our second momentum. Knowing the speed, we can find that momentum, and then our total moments. The only force that causes a moment is this component, the tangential component, which is perpendicular to the 4 feet. So the radius times the force times the time due to the integral is going to equal our final momentum, and we get our time. Alright, so just like when we had linear momentum, we did impulse momentum, and then the next lesson we did conservation of linear momentum, we also have conservation of angular momentum. So when there's no external forces or no impulses on our system, then angular momentum is conserved. Right, so that means that h1 is equal to h2 for all of the bodies in our system. So our procedure then is to draw our free body diagram, identify any axis that has no net moment around it, so all the forces pass through a point or are parallel to the axis, and establish the magnitude and direction of any initial and final velocities. Alright, then we're going to use our momentum equations, which would either be impulse and momentum or conservation of momentum to solve the problem. So let's take a look at an example where we're going to be using conservation of momentum. So we have a very large table, and on that table is a ball attached to a string. And that ball initially is at a radius of 1.75 feet, and it's moving with a speed of 4 feet per second. And that speed is tangential, right? All of the speed, it's moving tangentially. Then a force is applied to the rope, and that's causing the rope to get shorter and the ball to cycle into the center. And we're told that the rope is being pulled downwards with a speed of 6 feet per second, which is going to be giving our ball an inward velocity of 6 feet per second and changing the tangential velocity from our 4 feet per second to some other speed. And that's what we're going to be trying to find. So, part A, we're going to try to find the speed of the ball at the instant that r gets to 0.6, so it's very close to the center. And in part B, we need to find the work. If we're dealing with work, we're going to have to go to our work energy equations. So, first we're going to use our conservation of momentum to find the speed, and then we're going to use the work energy to find the work. So, what do we know here? Initially, we have a radius of 1.75 and a speed of 4. Those are ones. Then there's an applied normal velocity of 6, and eventually we're going to end up at r equal to r2 equal to 0.6, and we're trying to find v at 0.6. So v is equal to vn squared plus vt squared. Vn squared is already given, that's 6. So really our task is to find vt squared, or vt. So let's look at our conservation of momentum. h1 is equal to h2, because there's no external forces here that's going to cause an impulse. There's no forces in the direction that have a component in the direction of the 4 feet per second. So we have then R crossed with mv, those are the ones, is equal to R2 crossed with mv2. The mass is the same. The mass of the ball doesn't change, so the masses cancel. Our initial radius is 1.75, and our initial tangential speed is 4. Is equal to our final radius is 0.6, and our final tangential speed is what we're looking for. So v2t is equal to 11.67, which makes sense, right? As we're pulling this in on a shorter and a shorter rope, it is getting faster, which is what we would expect. So that means we now have the 11.67 here, which gives us a speed of 13.12. Okay, so we just found the speed. Now let's do part B. So for part B, we're going to use our work energy equations. So work energy said that T1 plus work from 1 to 2 is equal to T2. Well, T1, kinetic energy, is 1/2 mv squared, v1 squared. The work is what we're looking for, and T2 is 1/2 mv2 squared. Well, m is 0.8 divided by 32.2, so 0.8 divided by 32.2. Our initial speed was 4 squared, plus the work, 1 to 2, is equal to 1/2 of 0.8 over 32.2, times our final speed, which is 13.12, right? We're looking for the total, the magnitude of the speed, not the components of the velocity squared. So we can solve for the work, which turns out to be 1.94, and the units are pound-foot.